So in this video, I want to go over, obviously, the answers to the questions in the multiple choice and in the FRQ. But more importantly, I want to show you how to get to the right answer and highlight the principles that I've used to come to the correct answer so you guys know what to study and to freshen up on. So looking at question 1, so for each one, you could go through the long process of looking at each stereoisomer. And so what you're going to do is you're going to have to first, let's look at compound X. You look and find the stereocenters. And then you're like, what are the possible combinations? One of those could be a wedge and a wedge. And then one of them could be a wedge and a dash. And then another could be a dash and a wedge. Because we're just doing, and so we look at those isomers there. But we don't need to go through and find all the isomers here, because we want to find one that is a Meso compound. And a Meso compound has two components that you have to look for. Component 1 is it needs at least 2 stereocenters. And so we got that right there, 2 stereocenters. And then the second component, is there a plane of symmetry that cuts that molecule directly in half, giving equal halves? The last two, if I try to draw a plane through here, do you notice how this side and this side of the molecule look completely different? Because one has a wedge, one has a dash. In contrast, if you draw a line through this first one, do you notice how this half is identical to that half? So that makes that compound a Meso compound. So that's the one that we want to take a look at. That's Meso. And then we have to take a look at the other molecule, molecule Y. And with molecule Y, we notice that there's a stereocenter, there's a stereocenter. It's kind of just like the other molecule. And so if we draw it out, we would have a wedged methyl, a dashed methyl, wedged methyl. And I'm just going to go wedge and wedge. Why? Because those are still stereocenters, but I'm trying to draw the molecule in such a way that we can get a plane of symmetry that makes each half identical. And so if we do that and we get an identical or a plane of symmetry through compound Y. So that means compounds X and Y are both Meso, and they're both achiral because they have a plane of symmetry. So for question 1, the answer is C. Question 2, Dungeons and Dragons problem here. It says, which of the statements are true? So let's go through each question there. A says the R dragon rutol and S dragon rutol have different melting points. That's false because enantiomers have the same melting point. B, a 50-50 mixture is going to be optically inactive. That is a correct statement. R does not rotate plane polarized light. That is false. Okay, because we're in the problem, it's telling you that they're enantiomers. And enantiomers are going to rotate plane polarized light. And then, let's see, D, S and R, dragon rutol, rotate light in the same direction. No, they do not. Enantiomers rotate plane polarized light by the same magnitude, just in opposite directions. So answer B is correct. Which of the following alkenes only has an E configuration? So in general, when we have an alkene and we have these substituents here, Z, Y, X, and let's just go P, remember what we do? We focus on just one carbon at a time. We have an X and a P, directly attached to that green carbon. And so we asked the question between X and P, which one has the highest atomic mass? And these are all hypothetical. Let's just say X has the higher atomic mass. Then we go to the next carbon in that double bond and then ask the question between Z and Y, which has the largest atomic mass. And let's say we say Y has the largest atomic mass. Now with respect to the double bond right here, you can see that X is on top, Y is on bottom. That makes them on opposite sides, giving us the E configuration. Okay? So we're going to use that same principle now with these molecules here. So we have a chlorine versus a carbon. Which one's larger? Clearly the chlorine. Then we come to this carbon right here. What are we comparing? There's a hydrogen. Carbon or hydrogen? Which one has the larger atomic mass? Clearly the carbon. Do you see how both those circles are on the same side? So that would be a Z. Come here. This one's going to be higher priority. For this one will be, those will be higher priority, making that Z. There's our carbon. Fluorine versus carbon. Fluorine is larger. And then this carbon right here, this one might be, yeah, let's draw this one out. Let's do this. So we are comparing this carbon versus that carbon. Which one's going to take higher priority? Well, let's do the top one first. What's directly attached to that carbon with the arrow? Put it in parentheses. Directly attached to it is a oxygen, a carbon, and 2 hydrogens. Whereas the arrow on the bottom, what do we have? We have 4 carbons attached to the carbon with the arrow. And then when we compare oxygen to carbon, we see oxygen has the largest atomic mass, making this group right here the higher priority. Hence, compound 3 is going to be a Z. Then when we come to the very last one, there's our carbon. That will take priority over the butyl. And then we have a hydrogen here we need to highlight. And a carbon takes precedent or higher priority over hydrogen. And so what we have is the red and the green circles are on opposite sides of those double bonds, making this guy a E for opposite sides. And so that would have to mean that D is the correct answer. Question 4. Which statement best distinguishes homolytic cleavage from heterolytic cleavage? If we look at a hypothetical, X bond, Y bond. A homolytic cleavage is 1 electron goes to X, 1 electron goes to Y. So now we are going to generate 2 radicals. In a heterolytic cleavage, one of those atoms, X or Y, typically the more electronegative atom, is going to get all the electrons within that bond, which then would make Y positive, and then X is going to have those lone pair, which then would make that guy negative. So we have a cation and an anion. And as you look through the answer choices, the only one that makes sense would be C. Bond dissociation energies to figure out the heat of the reaction. So in order to do this, we need to figure out which bonds are breaking. Which bonds are breaking and which bonds are formed. So this bond right here, the carbon-bromine bond is breaking. And a hydrogen-oxygen bond is breaking from water. Because we see this carbon right here is that carbon chain right there. And so this bromine is no longer there. So clearly the bromine had to have broken off. And then the oxygen atom right here has 2 hydrogens. And then when it goes to product, the same oxygen atom now only has 1 hydrogen. So an oxygen-hydrogen bond had to have been broken. So the bonds that are formed would then be the carbon O8, or the oxygen bond, this one right here. This carbon-oxygen bond is being formed, and then we are forming a bond between the hydrogen atom and the bromine. That bond right there is being formed. So when we go and look at our tables, we want to find a species that looks like this to figure out the energy associated with breaking that bond. And if we scroll up, we will find our molecule, and we have to be very careful because this one has carbon and a bromine, and this has a carbon and a bromine. So we have to look at those condensed structures and make sure that those match our molecule. Okay? And so this one up top would represent our molecule of choice. And then where's the one that water? Right there. So those are the 2 that are the energies that are going to need to be used to calculate how much energy to break a bond. And when we break a bond, that's a positive energy. And then we need to find the species with the, let's double check, the OH bond and the HBr. So we come here and try to find HBr. There's the HBr. Then we need to find the carbon-oxygen bond. Okay. Let's see here. What's interesting here is that is not our product. That is not our product. That is not our product. This one is. But fortunately, look at the answer, the values. They're all the same. But if we're being precise, this was the one that you would zone in on and be like, oh, 381. So when you have all those, since those bonds are being formed, those values that I just barely circled would have to be negative. And so that leaves us with answer choice A as the correct answer. Question. So this is just understanding the principle of entropy. Entropy means more disorder. And so when a molecule is within a ring, its ability to rotate and twist is reduced compared to a linear molecule. So we see molecule 1 and 3 are both ring structures compared to structure 2, which is just a linear molecule. It's just drawn in such a way that it kind of looks like a ring, but it's not a ring. It's just a linear molecule. So molecule 2 has the most entropy. And so going from molecule 2 to molecule 3 is a decrease in entropy because it's being restricted. So when we have a decrease in entropy, that's going to be a negative entropy. So answer choice B. As the problem reminds you, a fast reaction is looking at the rate determining step and how steep or how big that step is. What I mean by big is you're looking at the starting materials. These are all the starting materials right here. Okay? And we are asking, in that first step there, how big is the hill that it needs to climb? And so in chart 1, we have to go from there to there. Starting material to the transition state. And so that is the energy gap that it has to overcome. When we look at 2, we have to overcome that energy gap for this reaction. So comparing 1 and 2, we see that 2 would be a slower reaction because that energy gap is much larger. And that energy gap we call the energy of activation. So now we're just simply looking at all of these and trying to find the one that has the smallest energy of activation. And that would give us the fastest reaction. And so upon close evaluation, you will see that this gap right here is the smallest. So that makes answer choice E the correct answer. Question 8. Which transition state resembles the structure of the product? So what we're trying to look for is looking for the transition state and how close in energy it is with respect to the reactants and the products. So these are the starting materials or the reactants. Those are our products. And on the y-axis is numbers. So we have a value associated with starting materials. We have a value associated with the transition state. And we have a value associated with the product. So we just have to ask ourselves, with respect to the transition state, which one is it closest in energy to? If this is the transition state, that's the product, that's the starting material. Do you see how the transition state is closer to the products? Right there? In terms of energy. Whereas if you look at the structure or the reaction Y, our starting materials are there, transition state is there, and our product is right there. Which one is the transition state closest to? Right there. That energy gap is different, much smaller than this energy gap. So the transition state that resembles the product is going to be X. And this principle is using Hammett postulate. So we got X as the transition state that looks like the product. Then the second part of the question, which energy diagram represents an endothermic reaction? That is when the product is higher in energy than the starting material, which is also X. So the correct answer then would have to be B. How would we solve this problem? This is a problem that's looking at the relative stabilities of carbocations. So if we rank these, the first one is secondary, tertiary, that one's tertiary, and this one is secondary. Okay. So if we take a look at molecule 1, we see it's secondary. And so we look, is there a situation in which we could do a hydride shift or an alkyl shift to make it more stable? And there is a hydrogen there that if it would shift over like that, we would now get a product or a carbocation that looks like this. And now it has gone to a tertiary carbocation. So molecule 1 is going to rearrange. Molecule 2, if it rearranged here, if it took one of these hydrogens and shifted it over there, what would we have gotten? We would have gotten this. So it went from initially being tertiary to tertiary. Was there an energetic incentive for that to happen? No, there's not. So it's not going to do anything. So compound 2 is just going to sit tight. No shifting or rearrangements. let's jump to molecule 4, because all we have are hydrogens here that can do a hydride shift. And if I picked any of those 4, we would get something that looks, we would just shift the carbocation over. So that is also secondary. So molecule 4 is not doing anything. Now, what's interesting about molecule 3 is, do you remember how we have something called allylic cations, which are really, really stable? So molecule 3 has a tertiary carbocation. That is true. But look at what happens. What if we did a methyl shift? Let's take this methyl right here and shift it over. Okay, when we shift it over, we're going to have this species right here. We're going to have 2 methyls there and 1 methyl here. And now where did the carbocation go? It went right here. So what did we do? We went from a tertiary carbocation to a, what most people would call, another tertiary. But it's more than a tertiary carbocation. It is a tertiary allylic, because it is adjacent to that double bond, that pi system right there. So comparing these 2 tertiary carbocations, the one on the bottom is going to be way more stable because it's a tertiary allylic cation. And so it has an incentive to rearrange to get to something more stable, and so it will. So the answer choice for question 9 has to be D. I'm hoping that you guys are seeing how I'm using principles to come to a conclusion. And so in that problem there, I'm just looking at relative stabilities of all the types of carbocations that you have been taught. Okay, when we name this, what's our objective? Step 1 is find the longest carbon chain. So if I go 1, 2, 4, 5, 6, 7. 7, so that would be heptane. Can I find a longer one? 1, 2, 3, 4, 5, 6, 7. And then if I did this 1, 2, 3, 4, 5, 6, and 7. So doesn't matter how I draw it out or trace it, we are going to get 7 no matter what. Now the question is, which color is going to win out? And the one that we can take off the table right away is the red numbers, because when you number those 1, 2, 3, when do you bump into your first substituent? At carbon 3. But when you look at the green and orange numbers, when do you bump into your first substituent? Carbon 2. So the red one is out based off of that rule of giving the substituents the first, when you're trying to find the longest carbon chain, you want to give the first substituents you bump into the lowest locant number. And so now it begs the question, which one between green and orange? And the answer is they're exactly the same. So it does not matter. So let's just stick with the green for right now. Now, why don't we number it this way? 1, 2, 3, 4, 5, 6, and 7. In that order? Well, because of what we just talked about. If I numbered it from left to right, then I don't bump into my first substituent until this carbon right here. So numbering it from right to left bumps into that red. No, bumping into this substituent when we number it in this way. Okay, so what is our substituents? We have a methyl, ethyl, and a chloro. So we need to find those. So we have a 2-ethyl. We have a, not 2-ethyl, 3-ethyl. We have a 2-methyl. And then a 3-chloro. The parent name is 7 carbons long, so that makes it heptane. That's the parent name, or said another way, the longest carbon chain. So now we just have to put this all together in alphabetical order. And C comes before E, and E comes before M. We'll write that all in alphabetical order. We would see that we have answer choices here between B and C. 3-chloro, 2-ethyl, no, 3-chloro, 3-ethyl, 2-methyl, heptane. So both of those look correct. But now we have to find the stereocenter right there and figure out if it's R or S. Chlorine takes priority 1. Carbon 2 takes priority 2. Carbon 4 takes priority 3. And the ethyl group is going to take priority 4. We ignore the lowest priority and just trace 1, 2, 3. We are going in the counterclockwise direction. The lowest priority, the ethyl group, is a dash, so we leave everything alone. And so counterclockwise makes it an S. And so that means answer choice B would be the correct answer. Question 11. First, we need to understand what kind of reactions happening here. And so I like to draw that compound right there. I look at the answers briefly and see that the carbon chain is written for the first 3 or 4 problems. That's written in that manner. So I'm going to just go with that. Okay. 1, 2, 3, 4, 5, 6. Now where's the, in my molecule that I've drawn, where's the iodine going to go? That's 1, 2, 3, 4, 5, and 6. It says 4-iodo. So I would have to put that on carbon 4. And I'm going to start it off with a wedge. And the 2-methyl part is right there. Now I just need to double check. Is the starting material? It says it has to be an S. So did I draw the S? Iodine priority 1, 2, 3. The hydrogen that's dashed is priority 4. But I'm not going to worry about that because it's on the dash. 1, 2, 3. That is definitely S. So I've drawn the S enantiomer of the 4-iodo 2-methylhexane. This is our attacking species right here. When you look at that attacking species, you see that it's ionic. So that means sodium plus, SH minus. So the attacking species is a strong attacking species, which favors E2 and SN2. The alkyl halide right here is a secondary alkyl halide, which favors all 4 mechanisms. The carbon that it's attached to is sp3 hybridized, so it can do a reaction. There's nothing about solvent. There's nothing about heat. So we got to use the information that is given. We can't just make anything up. The concentration of the reagents are strong or are concentrated because it doesn't say anything about a dilution. And then, so if that's where we stay, okay, that's where we're at. So we're thinking SN2 and E2. But then we take a quick look at the answer choices, and you can see that there are no alkenes, no elimination products. So this problem is kind of guiding you to the correct answer. E2 is off the table. So now we know it's SN2 and what's the important feature about SN2 reactions. Backside attack. So the attacking species, the sulfur, negatively charged, is going to come in and attack carbon 4. Backside attack, meaning it's coming in as a dash. Then the iodine is going to fall off. It's a good leaving group. And so we are looking for something that has a SH coming in on the back side. Okay. So this has an SH, but it's a wedge. That meant it came in from the front side, or the same side that the leaving group is, and that cannot happen in an SN2. This has a dash, but it has a methyl attached. There's no methyl here, so that one's out. Okay, and so the only answer choice left would have to be that guy. That makes any logical sense to do an SN2 reaction. So that would be answer choice B. Rank the compounds for the most reactive. In order to do this, what features do we look for to look at how fast an SN2 reaction looks at or behaves? Is the strength of the attacking species. But there's no attacking species shown. All we're left with is the alkyl halide. And so you can see alkyl halides here with some leaving groups. And we have this chlorobenzene right here, which it's not going to do an SN2 reaction at all. Why? Because the halogen is attached to a carbon that is sp2 hybridized. So that's not going to react. So that would be our least reactive. And between a primary alkyl halide, secondary, and a tertiary, which goes the fastest? Or which is the most efficient? Primary. And so that's a primary, that's a secondary, and that's a secondary. So we found the most reactive and the least reactive. Okay. But then how do you break the tie between carbons 2 and carbon 3? Well, they're different leaving groups, right? Chlorine versus the bromine. Which one's the better leaving group? That guy. So that's going to make that reaction go faster than compound 2 due to having a better leaving group. So the correct answer would have to be C. Because that 1 is the most, 4 is the least, 3, then 2. Yep. So answer choice C. Compound 3, 13, I mean. When we take a look at this, we find a good leaving group. The good leaving group is attached to an sp3 hybridized carbon. So that can do a reaction. We also find that that is a secondary alkyl halide, which means all of the reaction mechanisms are possible. We see that there's no solvent mentioned, but there is an attacking species. You see that's ionic. So we have something that is negatively charged. So that would mean that is a strong attacking species that favors SN2 and E2 reactions. When we take a look at the answer choices, there are absolutely no substitution products. So once again, this question is designed to really narrow it down for you to which mechanism it is, and it's going to be an E2. And so then, what are the features of an E2 reaction? You have to have anti-periplanar hydrogens to the leaving group. So we find the carbon that's attached to the leaving group, and then we look at the adjacent carbons. So we have alpha and then the beta carbons. And attached to the beta carbon on the left, we are going to have a dashed hydrogen, H1, and a wedged hydrogen, H2. On the beta carbon on the right, we are only going to have one hydrogen, that's a wedge, H3. So of these 3 possible hydrogens, there's only one that's possible. The only one. And you would see that this ethoxide, the negatively charged base, which is a strong base, can only go and attack H1. Because that's the only hydrogen that is anti-periplanar. So that would give this as our only possible product. Some people would have chosen this as the major product because students would use a principle that is a true principle. This would be a tertiary alkene, and this one would be a di-substituted alkene. And not tri-substituted. We have a tri-substituted alkene, which is more stable than a di-substituted. That is a true fact. If you compared these two products side by side, which one would be the more thermodynamically favored product? It would be compound 4. But compound 4 is only possible in this particular situation is if H3 was a dash and the isopropyl would be a wedge. But it's not. So the only possible hydrogen that can be attacked is H1, which gives us this as the only product. Okay. So when we look at step 1, what's happening? We are taking this and reacting it with the acid to put on a proton. So step 1 is a proton transfer step. Going from this molecule to that molecule, that's step 2. What's happening? The water molecule is leaving. So we have a leaving group that has left. And then from this to that, what is happening? We are removing that proton. And so if we did plus H3O plus like that, complete that whole step there, the water is coming in and removing that proton. So we have another proton transfer. So what does that give us? Answer A. Which of the following choices gives the rate equation for the reaction? It's telling us it's an SN1. So we have attacking species and the alkyl halide. We have 2 parts. So in the rate law, what is the most important thing? Or said a different way, are both of those things in the rate law or just one of them? And it's an SN1. And so it's telling us that only this is going to be in the rate law. That determines the rate determining step. So that would have to give us answer choice D as the only correct answer. Okay, now let's go and take a look at the FRQs. Okay. So if we take a look, another nomenclature problem here. What does that molecule look like? It looks like this. And then sodium chloride would be sodium chloride. Okay, but when we look at this energy diagram, that's really what's going to get us some points here. How many transition states are there? 1, 2. How many intermediates? 1. Which step is the rate determining step? When we do that, you have to look at the energy of activation for each step. So from here to the first transition state, we have the energy of activation right there, compared to this intermediate to that transition state. And you can see that energy of activation is much smaller. So whatever step has the largest energy of activation is going to be the slowest step. So what step is rate determining? Well, this from starting material to that transition state, or from starting material to that intermediate is step 1. And then from the intermediate to the product is step 2. And which step has the largest energy of activation? The red one. So that is step 1. How many steps are in the reaction? What you're looking for are how many transition states there are. There's 2 transition states, so that means 2 steps. And this is what we're looking for in the answers, those structures. And then, which mechanism is being used here? Well, we've given you guys hints. Look at the product over here. It says alkyl halide. Okay. So students who are drawing products that look like this or have an alkene, that is an elimination. But this right here is telling you that we're doing a substitution, that there's no alkene. Okay. So based off of that hint, E2 and E1 is just off the table. Now it's just between SN1 and SN2. And you can figure out if it's SN1 or SN2 by looking at the energy diagram. In this energy diagram, there are two steps. A SN2 has only one step. So that would be the only answer. Okay, now we have a transition state type of problem here. That's the correct answer that I'm looking for. You are illustrating in the red circle, shape, whatever you want to call it. I'm trying to see if you drew the molecule in the same plane. You're implying that it's in the plane and that the sulfur is attacking from one side and on the opposite side is the leaving group. And so that's what we're looking for in the correct answer. Something like that. Now the mechanism here, zoom out a little bit. That's the correct mechanism, step by step. So take a good look at that. And I was able to give some points if you had some of those steps in there somewhere. But I'm looking at it from a holistic point of view to see if you understand what's going on. And so I did my best to award points when it was merited, or when it was warranted. Yeah, I'll use that word. And then when we take a look at this last question, we can see that we have a tertiary alkyl halide. It's attached to an sp3 hybridized carbon, so we can do reactions with it. Here we have a bulky base. Here we do not have a bulky base. And so, how do I know substitution is off the table? Well, bulky base, what type of base? A strong bulky base, so that favors E2 only. That is a strong base that favors E2 and SN2. But why do I know SN2 is off the table? Why can't I not have an SN2 product? Because we have a tertiary alkyl halide. Tertiary alkyl halides cannot undergo SN2. And because this is a strong attacking species, SN1 is not on the table. Okay. So it's just E2 for both. And now if we do a strong bulky base, we identify the alpha, beta, beta, and beta. Betas 1 and 2 are the same thing, but beta 3 is less sterically hindered. So a bulky base is going to find the beta hydrogen that is less sterically hindered, hence B3. So if we draw in a hydrogen right there, the base, I'm going to draw as a generic base, will now come in, grab that proton, and kick that off like that. This is an E2, so does it still need to be anti-periplanar? Yes, it does, but we have 3 hydrogens coming off of here, and one of them is bound to be in the conformation that is anti-periplanar. So I'm not too worried about which hydrogen, as long as we came up with that product. That's what we're looking for. And then, if we use the smaller base, the sodium ethoxide, we then have to do the same analysis. We look at all the beta hydrogens, and since sodium ethoxide is going to be a slender base, it's going to find the thermodynamic product, which is the one shown there. So the one on the right would be the Zaitsev product. The one on the left would be the Hoffman. Okay, and so this one is for exam F. Let's just go through exam G. It's all pretty much the same thing here, other than the reaction is different. It's 2-chloro. Okay, 2-chloro, 2-methylpropane plus potassium bromide. The answers here are all the same. 2 transition states, 1 intermediate, first step, and first step. That's all the same right there. Now, how many steps are in the reaction? Wait, that all got changed up. Let's read the question. How many transition states? 2. How many intermediates? 1. Which step is the rate determining? Step 1. How many steps? There's 2 steps. Okay. So that's what it looks like. So class, I want you to be aware that if this was the problem that you were supposed to, or if this is the problem that you have, but all of a sudden you are drawing your alkyl halide right here, like this, and you put that in for your answer, clearly you're cheating. Because when you read the problem, there's no bromine there. The only way, if you were looking at your paper and your paper only, there's no way you could get a bromine in your alkyl halide at all. The only way you could get a bromine is if you're looking to your left or your right. So we're going to pay attention to that as graders. What mechanism? Same answer, SN1. Now, here's another thing. We've changed from, what was it, a bromine, I think the other one was? Yeah. See, they're just slightly different. So we can find the people that are being dishonest. Because I'm trying to level the playing field. And we want people to pass a class who know what they're doing. So the same as before, same idea, just with different starting materials. The mechanism right here is slightly different because we have a different substrate, but they have all the same steps. It's just the molecule looks a little different, okay? And we have a different attacking species right there. So that's what we're paying attention to, but that would be the correct answer. And then, same principle as in the last one, just different molecule. So this one on the left would be our Hoffman product. Whoops. And then the one on the right would be our Zaitsev product. Based off of the same rationale. There's our alpha, beta, beta, and beta. Okay? So I hope you guys find that helpful. And if you have any additional questions, look at the grade scope. It has the answer key for all the problems. So I know I only went over exam A for the multiple choice, but if you get on to grade scope, once it's been released, you will be able to see the answer key there. Okay?